Good morning. Please take a seat at your station. The contest start will be delayed because of the time needed to get everyone into the arena. So please wait at your station. Do not touch the envelope. Do not touch the computers and do not touch your reading materials. We will announce as soon as possible the contest start time. In the meanwhile, you can go to the toilet, but other than that, please stay seated at your stations. Thank you.
Good morning, everybody. This is Kim Schrijvers broadcasting live from IOI 2018 here in Tsukuba in Japan. And I know many of you are waiting for a scoreboard, and if you look behind me, we have a scoreboard up. And we can actually tell you the URL, and I will ask one of my friends in the room to type it in the comment section so you know about it. The URL is ranking.ioi18.net. So ranking.ioi18.net. So we're now allowed to actually give you that URL so you can look at it and see the scores. And if you look at the scoreboard, you will see that, there are some kids that have scored some pretty good scores already. There's Hua Young Tao, who is already at 131 points, but doesn't yet have a full score on the first task. So obviously, looking at the scoreboard, the task combo, which is an interesting task about finding out what the secret sequence is in a game, in a computer game with the buttons on a PlayStation. Obviously the easiest task, many kids scoring it, but he doesn't have the perfect score yet. There aren't that many kids that have scored yet on Seeds or Werewolf, although 2 kids have almost scored a 50% score on Werewolf. So what I'm going to do is we will show you the contest hall for about two minutes while we bring in one of my friends who will tell us all about the 3 wonderful tasks of today. So let's go to the contest hall. And good morning, everybody. We are still broadcasting to you live from IOI 2018 here in Tsukuba in Japan, where a typhoon is supposed to be heading our way tomorrow or in 2 days. But today, the only excitement comes from the competition hall. With me is my dear friend, and it's always nice to show how it's spelled, because otherwise, can we zoom in on this? You know, there you go. See, my friend Jacob with Wojski? Wonski. Yeah. It's a Polish name, and he is very important. You are very important in the ISC, right?
Well, I mean, I'm just one of ISC members.
Right. So you're very important for the whole competition, because the whole ISC is.
I mean, it's mostly the host running the competition. We're there just to, provide advice and then give tips on, what are our usual ways of dealing with some issues, and just sharing our experience from past years. But, in terms of the amount of work, is the host.
It's the host that does everything.
Yes.
So looking at the most important thing of this week, the questions. Is it okay if we go through the questions one by one with you?
Sure.
Okay, let's look at the question combo. So I have the question text on my screen, and I don't know if they're published on the web yet. But combo is a task about a PlayStation?
Well, it's about a video game.
It's about a video game. So please tell us a little bit about the task.
Right. So it's about a video game in which you can make a combo move, which just consists in pressing a sequence of buttons one after the other.
Like in the old Street Fighter, where BBAX, BBBBX
exactly.
Would give you... Okay, that's a combo move.
Yeah, and this is exactly the set of keys we're using. Like, a combo move consists of pressing buttons, and the buttons are A, B, X, and Y.
Okay, so that looks very familiar. To a lot of the kids, they'll probably be like, oh, that just feels familiar.
Yeah.
And what are we doing about these combo moves in this task?
So there is some kind of ideal move which is programmed in the game. So it's some sequence of those characters, which is initially not known to us. So
it's a secret.
Yeah.
There's a secret move, and then you win if you press and make that move somehow.
Yes, this is the goal.
So the goal is to find out what the secret move is.
Yeah, exactly.
Well, when you have to find something out, I'm guessing it doesn't make sense to just guess every possible move.
Sure.
So what would you do? What do you do, and what kind of information do you get back?
Right. So first of all, there is one additional assumption. This move consists of those 4 characters, but we know that the first character is different from all the others.
Okay.
It's just, well, otherwise solving it would not be very very easy. And then what we can do? Well, we can basically press a sequence of buttons and then see how many points we get for pressing that. And this is the operation where we can do.
Okay, so there are 2 things that I have a question about, obviously. One is, do you know how long the secret move is?
Yes.
So you know how long the secret move is, and how many buttons can you press?
So you can press any number of up to, I think, 8,000 buttons. Like, you can even press more than the secret move.
Okay, so if the secret move is 10 buttons, you can still push 8,000 buttons. But you get some information back.
Yes, so you get a number of points for making your sequence of presses. And now the key thing is how is this computed?
Right, so how do you determine the number of points when I press some buttons?
Right, so we like the short scientific answer is we take a look on the longest substring of the sequence we pressed. That is a prefix of the secret move.
Okay, so the secret move, say it's 5 characters, and if the first 4 characters in that order show up somewhere in what you've pushed, you get 4 points.
Yes, but they have to show as a contiguous
string.
Yes.
String. Okay, so there should be an actual substring. So the substring that is the longest substring, that's also a prefix of the secret code. That's and the length of that substring is your score.
Yes.
Okay, and so you're pressing buttons and you're trying to figure out, probably in as few presses or in as few questions that you asked?
It's the number of questions that one has to minimize, because well, in every question you can ask any number of buttons.
So if I can only, so first obviously I have to figure out what the first character is.
Yes.
So I can just do that by asking you one character, and you will say, yeah, I get either 0 or 1 point.
Yeah. So the easy way is to do it 3 times.
Right.
If all 3 times we got 0 points, then
it's
the fourth one. Actually, you can do this more efficiently.
Oh, how do you do it more efficiently?
Well, so you can. It's you're asking about the substring, so it's. I mean, maybe it's not very obvious if I just give you the magic sequence, but you can construct. You can think of some gadget. That like some very well crafted sequence that basically, depending how long is the overlap of this sequence with the secret string, we can actually deduce the first character, and I think just 2 questions.
Oh, that's impressive.
Yeah, and then you have to you need to construct like actually a long sequence of presses, which would basically covers many possible beginnings of the secret string. And
cool.
Then based on what you get.
But so we'll dive deeper into the actual solution in a little bit. So right now let's go to an example. Yeah. And so if the secret string is, I'm just reading from my screen just to make life easy. A, B, X, Y, Y. So the first character is an A, and you know that A never appears again in the string.
Right.
But everything else can appear as many times as it wants. So A, B, X, X, Y. And then if you press X, how many points do you get?
0.
But there's an X in there.
Yeah, it's the other way around.
It's the prefix of the other thing.
Yeah. So we're looking on the prefix of the secret string. That's a substring of what we press.
So the secret is still A, B, X, X, Y, and now I press Y, Y, X, Y, 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 A. How many points do I get?
You get 1 because the A matches that you press at the end matches the A, which is the beginning.
That's the prefix.
Yeah.
And so if I press AB, I get 2 points.
Yeah.
And if anywhere in the string is AB, I get 2 points,
unless
somewhere else in the string is ABX, because that would get you 3 points. So you get the highest number you can find. And how many kids did you expect to solve this problem correctly?
So we can see it's the easiest problem.
Well, it's obvious from the scoreboard. It's from the scoreboard. It's obvious.
Yeah.
But did you know this beforehand?
Yes. I mean, this was the assumption that it's supposed to be the easiest task for today. Not sure what the actual number is, but I mean, our estimates were probably above 80.
Okay.
But it's also true that our estimates are always wrong. So.
But that's why they're estimates.
Yeah.
That's why they're estimates. Okay. So question 1 is a simple question, first in line, and it is about a PlayStation game, whatever, where you have to press a combo of moves of A, B, X, and Y to figure out what the secret move is that's programmed into the machine.
Right.
And the secret move starts with either A, B, X, or Y, but the character that it starts with does not appear anywhere else in the string.
That's right.
And so it's the longest prefix that matches, that gives you some score, and you are told how long the secret is.
Yeah.
So you don't have to keep guessing, or is there's a longer one. Okay. Well, let's go back to the room for just about a minute so that you can check whether there's any emergencies going on, and we'll just bring up the next question. So we'll be back in about a minute or 2. Good morning, everybody, and welcome back to the IOI live broadcast from IOI 2018 here in Tsukuba in Japan. We are very excited that the contest has been going for a while now. People are scoring. The live scoreboard is up, in case you're interested, and we now actually have flags and country names there, so making it a little bit easier to track your own country. With me is my friend Jacob from Poland, and we are going to be discussing the tasks. And right now we'll talk about the second task of today, the task seats. And seats is a task about a programming competition. It's a meta task.
Yes.
So please tell me, what is Seats about?
Well, so we have a number of contestants sitting in a rectangular hall. So this hall has H rows and W columns. And basically, we can think of it as a rectangle divided into H times V 1 by 1 squares.
Okay.
And now the contestants have numbers from 0 up to number of contestants minus 1. And every contestant has exactly one seat assigned. Obviously, each seat has exactly one contestant sitting on it.
Well, you say obvious, but to some people that may not be obvious. But when you look at the contest hall, it is rather obvious. Okay, so we have we have a big rectangular hall of seats. The seats don't have numbers but have a coordinate. And then we have a bunch of contestants to fill up the hall completely. And the contestants are numbered from 0 up to n minus 1.
Yeah.
To fill up the whole hall.
Exactly.
Okay. And now we're asking questions, I presume.
Yes.
What are you doing?
So we can think of it as just a grid filled with distinct numbers, right? This is the way to picture it. And then let's fix a contestant number K.
Yes.
And now let's paint the cells with contestants with numbers up to K black.
Okay.
And keep the remaining cells white.
Okay.
And now, if what we get is just a single rectangle,
okay,
we say that the set of seats where these contestants are sitting is beautiful.
Okay, so I have a rectangle filled with numbers, and basically I'm looking at the numbers 0 up to K, where and so that and then the question is, are these numbers very compact in that rectangle where they themselves form a sub-rectangle of the whole thing?
Exactly.
So that's you're coloring them up so that you can easily tell, okay, so I've colored them up and this is a rectangle.
Yeah.
But there could be multiple of such rectangles in the big And am I correct that just having seat 0 by itself fits your definition?
Yes.
So the single seat is always okay, seat 0.
We say it's beautiful.
It's beautiful is the word. So
somebody must have liked rectangles.
Right. Yeah. Well, we're geeks. So seat 0 is beautiful. And everything is also beautiful by definition because it's a rectangle.
Yes.
So the goal is to figure out how many other beautiful rectangles there are.
That's right. So basically we're wondering for how many numbers K the contestants with, numbered from 0 to K, seat in a beautiful set of seats.
Okay.
Meaning just rectangular.
Right. Ooh, that's an interesting question. But you're making it more interesting because the contestants are going to be swapping places.
Right.
What's going to happen there?
So once we answer these questions, we have updates to the plan. Each plan just says, okay, now these two contestants are going to swap their seats.
Okay.
And after that, we want to answer the initial question once again.
Okay. So you have to somehow be smart that you don't have to recalculate everything.
That's right.
Because calculating it all, I mean, it takes time, but you could just have a stupid algorithm that just checks every value of K.
Yeah, so there are multiple levels. First, the simplest solution would be to simulate all of it, but that would not be fast enough. Then we can have a solution which just does it for the initial set, which is fine, if there are no changes, but it's not fast enough if we have changes.
Okay.
And then there is yet another step to make to support efficient updates when we have contestants swapping seats.
Nice. And we'll be talking about the solutions later today. So right now we're just giving you the question so you can think about it at home. And so this is quite clear. And this you think is the medium task of today. Yeah,
this is our belief. Of course, can be wrong. We're usually wrong estimating difficulty, but we'll see how
if you look at the scoreboard, Yeah, it's hard to tell
I mean,
on the scoreboard at this point
Well,
because
what I'm saying, it doesn't mean that, if you want to get some point, it's not necessarily, just the first thing to try. But if you want to get full score, then we believe that it's the medium task of today.
Okay, well that's good to know. We'll go back to the hole for half a minute and then we'll be back. And let's see if the people are actually paying attention back there. Perfect. Hello everybody and welcome back to IOI 2018, broadcasting to you live from Tsukuba in Japan. We're very close to Tokyo. We're in the center of Japan on the eastern side, I think, overlooking the Pacific Ocean. Well, it's about 70 kilometers away from here. Right now, we are about an hour and a half into the contest, and we're discussing the problem set. With me is my friend Jacob from Poland, and we will be talking about the third question of today, which is the hard one.
Yeah, we believe that solving it fully is probably the hardest one for today.
And it's not only a hard question, it's a question about werewolves.
Yes.
So it's a scary question.
Well, depends on whether you like werewolves or not.
Fair enough. What is a werewolf?
So a werewolf is, a creature that has two forms, a human form and a wolf form.
Okay. And does he, at the full moon he changes, or can this werewolf change when you want him to change?
Yeah, so initially, even at the task statement, we were saying, that each night the werewolf changes its form from human to wolf, and it has to be in the wolf form at the end of the night. But then we decided actually night is not important to explain the task, and there is no night anymore.
Okay.
So we just have a werewolf that needs to change from one form to the other form at some point.
Okay, so we have a werewolf. He is initially in human form, and when he wants to change, he waves his magic wand, and then his paw comes out and he's a wolf.
Yes.
Okay. Now we have a network of cities and roads, and he has to travel from one city to another city. And during that trip, he starts off in his human form and has to change exactly once into a werewolf, and then eventually end up in the final city.
Yes.
Now there must be something harder, because we all know about graph algorithms. Anyone can find this.
Yeah.
So tell me, what is the trick? What's the question? What makes it hard?
Yeah, so we have the cities numbered from 0 to n-1. And then we say that the cities with low number have low population, cities with higher number have higher population. So basically the cities are sorted by population.
Okay.
And then as a general rule, I'm gonna make it more formal. We'd like to avoid, or we must avoid, the cities with low number when we are in human form, and we must avoid cities with highest numbers when we are in wolf form.
So I have the cities sorted by population. The low population cities, you don't want to be there as a human. The high population cities, you don't want to be there as a werewolf. As a wolf. And in the middle, is there a group where you can just be in either way?
Yes, there is a group where you can be both. And in particular, the start and end cities are in that group.
Okay, so you're guaranteed that you don't die, the minute the problem starts.
Yeah, so, and then, that's right. And then also, it's also allowed to transform in the start city and transform in the end city.
Okay, but you can only transform once.
Yes.
So you start as a human in some city and that city is you're allowed to be in human form in that city. And you have to end in a wolf city. Is there always a possible path, or are you asking the question, is there a path?
That's a good question. I think this may not be guaranteed. Let's have a check. I think it's, solving the task with the constraints is not always possible. I'm not sure if there is this case where it's not possible because there is no path whatsoever, but surely it's sometimes not possible.
Well, there's always a path. The task description says that the graph is always connected.
Okay, so then...
the graph is always connected. You don't have to worry about that. But so the question is there a valid path, yes or no?
Yes, this is what you have to determine.
But if you ask that question, I can just throw a coin and I have a 50% chance of scoring a perfect score. Woohoo!
Oh,
No?
well, we thought about that.
Oh, what? So how did you solve that?
So, well, first of all, within every test case, there are multiple questions that you have to answer.
Okay.
So for every question, actually, you get 4 numbers.
Okay.
It's the starting city, the city that we want to reach, and then there is a number which says what is the number of cities with low population that you want to avoid. So basically, we want to avoid all the cities numbered from 0 to X.
Okay, 0 to L.
Yeah, it's
in
L.
the
Yeah,
task.
it's
Yes.
L. And then
As a human.
As a human.
And
yeah.
you want R to the end to avoid as a wolf.
That's right.
And how many questions do you ask each time?
It's up to like a few 100,000, I guess.
So my chance is 1 in 2 to the power of 100,000
Yeah.
of getting a perfect score.
Yeah.
That sounds reasonable.
Well, for a single task.
For a single task.
The test case.
Okay.
And then there are multiple test cases in a subtask, and you'll have to get all of them.
So you do have to actually make a decent effort on solving this.
I mean, yeah, basically, probably the probability that you get it right this way is similar to, just you smashing the keyboard and typing the model solution by chance.
Right, 0 basically. I mean, not 0, but
Yeah.
for all intents and purposes, 0.
Yes.
Okay. Well, I think this covers the 3 tasks of today. And you think this is the hardest task to solve perfect? You think
Yes.
people may be able to get some points? And that's always tricky, right? That's harder to predict where the kids will score some points.
Yeah, I mean, we can see that. I'm not sure what is the scoring, but for seats, what you can do, you can really simulate all of this, and consider every set separately and just check, is this a rectangle? For werewolf, you can, for every query, you can delete the cities that you cannot go to, and just check if there is a path in the graph. So there are some natural, easy solutions, but then there are also some intermediate and hard ones.
Okay. Well, thank you so very much for coming over. And it would be great if you would come back in about an hour and a half, and then we can discuss maybe the solutions so that the viewers at home can actually start working on this. So we're going to go back and show you the live view from the contest hall. The IOI ranking is up and running, so you can go to ranking.ioi18.net if you want to see the live scoreboard. It does have country names now, it does have the students in there, so you can see what's happening. The video will go back to the contest hall. So thank you for staying with us, and we'll be back in a little bit. Hello everybody, and welcome back to the IOI live broadcast. There were people asking on the comment section to please mention the constraints for the tasks. The good news is that the tasks are now actually up on the official website as well. So if you go to ioi2018.jp, then you can click on competition tasks to find the tasks, but we'll just walk you through the constraints here as well. So as you remember, there are 3 tasks at IOI this year, and task number 1 is combo. In combo, you have to guess a secret sequence of a game console where the buttons you can press are A, B, X, and Y, and so you can make many button presses and then ask what your score, how many keys of the secret string you have guessed in your string, and your score depends on how many calls you make. And the length of the secret string for 5 points, the length is always exactly 3 characters. And for everything else, there are no constraints except for we know that the length of the string is never more than 2,000 characters. You can get 95 points where there is a complex scoring algorithm that depends on how many tries you make at guessing the secret string. So That is the single thing you have to realize there. So that's for combo. There are not many constraints besides the secret is never longer than 2,000 characters. I'm looking at my screen now about the competition, the question seats. Seats is about the rectangle that's filled with the numbers from 0 through n-1, and you're trying to color every cell that has a number from 0 up to k. And if the colored cells themselves form a rectangle, then we call that a beautiful rectangle. And now we're looking at the beauty of your entire rectangle, which is, you know, the number of beautiful rectangles in there. Obviously, that number, you know, the number 0, so just painting a single cell with number 0 is always beautiful. And painting all the cells is by definition also beautiful, but in there can be other things. So you know that there will never be more than 1 million cells in total, and you score points based on the size of the whole rectangle. So you can score 5 points for rectangles with fewer than 100 cells, 6 points fewer than 10,000 cells, 20 points for fewer than 1,000 in height, less than 1,000 in width, and less than 5,000 questions. So every time you calculate the answer, the grader will give you 2 kits that swap seats, so 2 numbers that are changed in the rectangle, and you have to answer the same question: how many? What's the beauty of the whole rectangle at this point? And so if you just look at the task description, you can see you can get a lot of extra points. You get 33 points for rectangles where the height is guaranteed to be 1. And so the width is, you know, as long as you want it to be. And 30 points, there are no additional constraints. So that's the seats question. In the werewolf question, you're given a graph with cities. It's a connected graph, so from every city you can reach every other city. And the cities are labeled from 0 up to n-1. The number basically indicates the population in the city. And you want to go from city A to city B, where you start in one form, you know, the human form, and you end up in a second form, which is the wolf form. At some point you have to transform. As a werewolf, you can only travel in cities with specific numbers. When you're in the human shape, you're not allowed to travel in the cities with a low population, and anywhere else you are allowed to travel. And if you're a wolf, you're not allowed to travel in the cities with a high population. Now, exactly where that threshold is dependent on the question. So it will give you a lower and a higher bound. So it will tell you up to here you can be you cannot be a human, and from here on you cannot be a wolf. Now, if you look at the constraints for the subtasks, you will see that I'm just going through it here. For 7 points, there are never more than 100 cities. 8 points, there are never more than 3,000 cities. For 34 points, you're guaranteed that all the cities are in a line. So they're not in a line that's sorted, but you're guaranteed that all the cities are in a line. And for 51 points, so almost half the score, there are no additional constraints. And if you look at the scoreboard, you will see that a number of students have scored 49 points. So they've managed to solve the first 3 subtasks, and that last one is apparently really, really hard. Now, in about an hour, we will be discussing the strategies and the solution strategies for all these 3 tasks when our friend Jacob comes back to help us out with that. For now, we'll just bring you back to the live scoreboard and to the contest hall. If there are any questions, just write them in the comments and we'll see what we can do about it. So let's go back to the contest hall. Hello everybody and welcome back to the IOI live broadcast from IOI 2018 here live from Tsukuba in Japan. The International Olympiad in Informatics is a computer programming contest, as you may know. There is a field of over 80 countries participating at this contest. And we have a live scoreboard you can look at if you're interested at ranking.ioi18.net. But you can also find the scoreboard just by clicking somewhere in the menu on ioi2018.org.jp, right? ioi2018.jp will show you links to the tasks and the live scoreboard. We're exactly 2 hours in. We started a little bit late, about 40 minutes late, because it took a long time to get all the students into the contest hall. So every kid, before he gets in, needs to be checked that they're not bringing in any illegal materials such as calculators or computers or smartphones or other watches or gimmicks. So every kid was checked. Their badges were checked to make sure that they didn't have any secrets stuck inside their badges. And then once they were all inside the contest hall, because it had taken a while, a lot of them still had to go to the bathroom. So there was a little bit of queuing around the bathroom, which caused, about a 40-minute delay. So there were no technical issues. The only reason we're late is just because we have so many kids here, and it was underestimated how long it would take to check them all. If we look at the live scoreboard right now, and you can see it up on the big screen behind me, and I don't think you can really see that from there, but if you go to the live scoreboard in your own web browser, and I'm just going to do that on the computer I have too many computers here, on the computer on my left, we will see that Benjamin Chi from the United States of America has already scored 211 points. So we're only 2 hours in, and he has a perfect score on 2 tasks. What the ISC thought was the easiest task is combo, and if you look at the scoreboard, it's obviously the easiest task, which doesn't mean it's easy. It just means it's the least hard task out of these 3. And werewolf, which the ISC thought would be the hardest task to get a full score on. So this kid has perfect scores on task 1 and task 3, bringing him at 211 points. I know that a lot of people are viewing from Japan, and if you go to the live scoreboard, you can select countries, and then on the scoreboard on the left-hand side, as you can see behind me, it will show you the exact position of the team you're looking at. So if we look at Japan, we see that Masataka Yoneda is in shared second place together with Huao Yun from Singapore, and Yasatuka Hiraki is in 11th place. Well, the score, it's all still very compact. So except for that number 1 place by the American kid, everyone that has scored 100 points or almost 100 points on the easy task with some points on the other 2 tasks will be somewhere around second place. So don't read too much into that just right now. Just know that American currently in first place, and the question number 1 is the easiest question to solve. Number 3 is what the ISC thought would be the hardest task, but of the other 2 tasks, it's the first one where someone gets a perfect score. The highest score on Seed so far is only 37 points, whereas the highest score on Werewolf, obviously 100 points, a perfect score, but a lot of kids scoring 49 points. We looked at the constraints of the tasks earlier, and 49 points is exactly a subtask boundary. So it means that all of the easy subtasks have been scored perfectly, and then the remaining 51 points are awarded to the best and perfect solutions. So it's a big jump from 49 points for that third task to 100 points. What we're going to do is we'll show you a couple of minutes of the competition hall, and then we'll wait for our friend Bernard Blackham from Australia to show up, and we'll do an interview about him, about all the technical things that are going on behind the stage. Because, 300 computers, 300 kids, but we also have a lot of grading machines. Whenever a kid submits a problem, it needs to be graded by a computer. And we don't have one computer grading all the kids, because then they would have to wait for a long time. So there are almost as many graders as there are students. We'll go back to the contest hall, and hopefully Bernard will be here very soon. Hello everybody and welcome back to the live broadcast from IOI 2018 here in Tsukuba in Japan. We are now in a conference center right near the Tsukuba main train station, which has a 50-minute direct train to Tokyo. With me is my dear friend Bernard Blackham from Australia, from down under. It was a short flight for you this year, right?
Hey. Oh, it wasn't that short a flight. It was 11 hours. But the big change this year, it was a single flight, which is unreal for us.
Direct flight.
Yep.
And almost no time difference.
No.
Barely. Not even worth talking about.
It's like the Brits complain about jet lag when they go to Paris.
Right,
Yeah.
exactly.
Yeah.
So it's that little.
Yep.
So you are helping out organizing the IOI.
Yes. I'm in the International Technical Committee. Our role is to kind of help the hosts with all the technical aspects of the IOI, things like the networks, the servers, all the boring nuts and bolts that a lot of people just...
Are you involved also with the ranking website? Or is that
Not directly.
Not directly.
Not directly.
Okay, because we know that the ranking website at this point is down, and we're waiting for it to get back up and running. And once it's up and running, we will let you know immediately. And if we notice it while we're not talking here, there will be a little banner up on the screen here that will say it's back up, so we can all check it again. The last time we checked, there was an American kid in first place.
Fantastic.
With a perfect score on 2 of the tasks. Wow. Anyway.
Lots of perfect scores, but yes, go on.
It is good. Technical things. How many contestants are there here? Approximately.
Approximately 340 contestants.
340 contestants.
Yep.
How many machines do they use?
So they each get a machine each for themselves.
Mm-hmm.
We have a bunch of spare machines in case
And what's a
machine
bunch of spare
fails.
machines? 1, 2, 10?
5-10%, so yeah, 10,
10%?
15. Yeah,
So that's 30 spare machines.
roughly. I
That's
don't have the exact
reasonable
numbers,
number.
but that's kind of what we expect.
Okay.
For like machines fail for all sorts of reasons. There might be the machine itself is a failure or the network connection to it.
Does it ever happen during the IOI that a machine fails?
Occasionally, yeah.
So
I think
every IOI 1 or 2,
if
or
there's generally like a 1% failure rate. So out of 300 machines, you kind of expect a couple
Okay.
might have a problem.
Okay, fair
Some
enough.
years are better than others.
Okay.
These machines are all quite new, so we don't expect many failures.
And these are all brought in by.
I believe they've been sponsored by Acer.
Okay, so Acer brings in all the machines.
Yes.
That's lovely.
Yeah.
So you have 340 actual machines that they're working on, plus say about 30, 40 spares.
And a whole bunch of working machines. So the machines which the solutions get graded on are the exact same spec laptop. And so there are, I think, around about 80 machines set up downstairs as well, whose role is just simply to run all the submissions that the students write.
So every 4 students basically have, for every 4 kids, you have 1 working machine.
Yeah.
Are you using the spare machines that are in the contest hall also for grading?
Can't tell you this year. It varies from year to year.
Okay, so
generally not, because
generally
we
not.
just want them ready to go.
Okay.
In case it needs to be swapped in.
So you have about 80 extra machines, and you call those the workers.
They're called the workers. Yeah.
And so a student submits a solution. He writes a program. He sends in the program. What happens?
So this year things are working a little bit differently. What happens is their solution gets transferred to the contest web server, and the software there will figure out what to do with it. Firstly, it compiles it, figures out does it even build. A lot of students sometimes submit code that we call it optimistic submission. They don't even test it locally because they know that they're pretty awesome, and sometimes they are. So they'll just submit it, and the code may or may not build.
You don't penalize kids for that?
We don't penalize them for
Okay,
that.
so they can
it's
just
also-
submit, but it counts as a submission. Because they only have a limited number of submissions.
I need to check the rules on that.
Okay.
I suggest you check the rules too. but,
Okay.
Yeah. Assume it compiles, it then, for each task, there are some number of test cases that we execute their program on. And these, normally, I think the time limit on the tasks vary between 1 to several seconds, and they get sent out to all the different machines. And if the queues are idle and all the machines have nothing to do, then we'll judge their solution in parallel on all the machines.
In parallel?
Yeah. So if there's 100 test cases and 100 workers, then in theory we can do all of them in parallel.
How does every worker know which test case to test?
There's one server whose job it is to distribute the tasks to all the
Okay, so
workers.
when you say you distribute it to all the machines, it's basically saying, okay, you judge this solution on task case 7.
Yeah.
And then send it to the other one, judge it on task case 8.
On test case 8, yeah.
So you don't tell them all, just, good luck and the first one to finish, we'll just take it?
Interesting idea, but no.
Okay, I'm just wondering.
Yeah.
So it gets distributed to these 80 machines over a network
Yep,
that you're in charge of.
nominally. This year, things are a little bit different. One of the big changes this year is that the hosts were under very immense time pressure to set up the competition hall. And what typically happens in the IOI is all the servers that do all the judging and all the management are all local inside the competition hall. This year, a lot of the services are sitting in a private cloud infrastructure in downtown Tokyo. And
Exciting.
yeah, it's radical. We had long discussions in kind of the planning meetings about whether this was a good idea and what kind of redundancy we need in place to make sure this happens reliably and we can withstand all sorts of
earthquake?
failures. Earthquakes, typhoon,
But the typhoon won't come in until 2
whatever
days
throws
from
at
now.
us.
Right.
Yeah, so day 2, we'll see.
We'll the scary one. Okay.
Yeah, so that's the new thing this year. It shouldn't have any visible difference to the students
But
at
the
all.
workers are still here.
The workers are all here.
So what did you outsource?
That server I was telling you about that manages
The
who should
distribution server.
distributes the test cases to each task.
Okay.
The scoreboard, all those services
Okay.
are pre-configured so that they were set up well in advance of the IOI.
Okay.
So they didn't need to move, they were ready to go.
Okay.
And the only things that needed to be set up on the competition hall were the workers and the students' laptops.
Okay.
And I've heard from several sources now that the entire setup was done in less than a day, which in IOI history is a tremendous achievement. It's never been done.
I've seen you set up the contest hall in Australia.
Yes, we set it up in 2013, and that took us the good part of a week.
That took you a whole week to set it up.
Yeah, and it's one of those things where you have your plan of exactly how things will occur, and it should have only taken 2 or 3 days. You spend one day laying your tables and your power and your networking, and then you have the plan, and then of course something goes wrong.
Right.
And everything is a bottleneck.
Yeah, it has to wait.
It's a
because
critical
you
part.
can't put the network equipment in until you've put the cables in, and you can't put the tape over the cables until the cables are there.
Yep.
Yada yada yada.
And you can't do anything about testing the machines until the entire network and power is
Right.
in place.
Okay.
So a lot of years there's like one minor hiccup, and that
Okay.
delays the setup by 6 hours or a day
Okay.
until it gets resolved. And so
Right.
we've normally had quite a bit of leeway. And this year, yeah, the hosts, I believe, only got the venue kind of a few days before the competition started. So
Okay.
there was immense pressure to avoid anything unnecessary. And so one of the things that was deemed unnecessary was the servers, which they don't need to be on site so long as the link is reliable.
And the
So
link is reliable.
the hosts have gone to great lengths to make sure there's redundant links between here and the cloud infrastructure.
Okay.
So we can lose one and it'll just fall back to the other.
And what happens if we lose both? Then contest dies?
We have manual procedures for if both fall out, but it's
Like back in
entirely
the days
unlikely.
where people have to walk around with floppy disks.
Not that bad, but just about.
Okay.
If everything goes down, we've made it clear to the students what they should do,
Okay.
and just save all their submissions locally. And there is a plan in place. I don't expect it will happen.
hoping well, definitely not today.
Yeah, it's one of those things where you should have a plan in place in case the unforeseeable happens.
Right.
It always,
Okay.
yeah, it's always a wise idea.
And so when I walk around the venue here, I see cables duct taped to the floor everywhere. This venue is not really laid out for an event like this, is it?
It's the internal networking is very much brought in by the hosts. It's, I believe, 2 days before the competition, someone told me it was a badminton court. Badminton courts don't need this level of networking infrastructure,
Right.
generally speaking.
Yeah, but so all around all the doors, there's a little fiber optical cable going.
Yeah.
So how many printers do you have?
You ask all the hard questions. I saw the room with the printers. There are at least 4.
Okay.
It could have been more in the background.
And then, so I remember at some IOIs when kids print something, there's a page before their print that actually has a map of the contest hall with a little cross where the print has to be delivered.
Yep.
Is that the same case here? These are not hard questions. I'm just very interested.
I've been focusing on a lot of other technical aspects, and I haven't.
Okay.
The
So
printing.
we can go back
it's
to
not my
well,
area,
printing
so-
sounds technical. But
It does.
how many switches do you have? That's technical. Which technical things do you do?
We've been helping out, guiding the software running on the machine, the CMS software that's judging all the tasks. One of our team members was responsible for making in the competition, students can now see statistics.
Yes, the little bar chart of
how many points have been achieved.
Right.
Oh, yeah. What proportion of points were achieved on each task. And so we've been helping to integrate that into the CMS software and lots of little things. The majority of the work has been done by the host, and so we've been largely kind of helping where we can. The IT series roles vary from year to year. This year the hosts have been very thorough and very diligent in covering all the bases.
Were you involved with the contest image that the kids get to work on?
Not the creation of it, but some of the debugging.
Oh, are there? What kind of issues do you run into?
So we found that code blocks apparently is one of the current popular complaints, that code blocks is buggy and crashes and
The IDE.
the IDE, yeah.
Okay.
And so I tested it for a full hour yesterday trying to make it crash on my laptop, and I couldn't do it. So I've been trying now on the contest machines to reproduce it, and so that's one of the things I'll continue doing when I walk away.
Okay. So the contest environment was published before the IOI?
Yes.
And kids were given a deadline to test it, and they, if they wanted extra software on there?
Yep.
Do you get any responses? Are there any kids requesting any weird software on there?
Often there is. A lot of the requests always come too late because people don't realize. It's one of those things where you expect everything to be there that you've seen before, but if something's missing, then you don't realize until it's too late.
Right, so they don't test. They're like, oh, last year was fine for me, so I'm not going to test it this year, and then your IDE is gone.
Yeah, and so one of the students asked for a Office editor like Word or LibreOffice or something so that they could print lined paper. And LibreOffice isn't in the image, but they didn't realize until the practice session, and by that point they weren't willing to take the risk to make changes to the contest image unless there were kind of pressing reasons why things were broken.
But it makes sense, right? You don't change anything the night before the contest.
Absolutely, unless you absolutely need to.
Unless you absolutely need to.
Yeah. If they'd raised it a few weeks out, I'm sure it could have been added to the image quite easily. So.
Right. Okay. Well, is there anything else you'd like to talk about?
I think I have a code blocks issue to fix, if you don't mind.
No. Go fix the... Well, I mean, you can't change anything in the image anyway now, but you will have to reproduce the issue so we can see if we can fix it for day 2?
For day 2, yes. If there's a simple enough fix, we've looked at the Ubuntu bug reports for code blocks, and they're quite extensive. If there's a simple enough fix that can be applied, we'll try it. Otherwise, it's up to the host to decide whether they are willing to undertake the risk.
Okay. Well, thank you for coming onto our show.
No problem. Thanks.
And good luck with the code blocks issue. And if you're still watching us from home, we are still broadcasting to you live from the IOI here in Tsukuba in Japan. We know that the ranking system, so the score server internally is working, but there are no scores published on the web right now. So we don't really know what's going on because we're not allowed to wander around wherever we want to. But we will try to find out for you what the current scores are. And as soon as the scoreboard is back up and running, we will let you know. With me was Bernard Blackham, a member of the ITC, who is in charge of all the things that he calls technical, which are more software technical than hardware technical. So I was asking some question that he did not know the answer to. But we'll try to get you all these questions, all the answers as well. So we'll go back to a live view from the contest hall so you can see what's going on there. Thank you for being with us. And good afternoon, everybody. Welcome back to the IOI live broadcast. We actually have a scoreboard. We realize that the official scoreboard at this point is down, but behind us, you can see the scoreboard. And what we're going to be doing is, maybe I should just move my head away a little bit, this way, and I will just slowly scroll down on the scoreboard while the camera zooms in on it. Aren't we special people for you? So at this point, in first place, with almost 3 hours on the clock, is Benjamin Shi from the USA. And we've just seen a change, where from Malaysia, Zizong Yeo has also scored a perfect score on Werewolf. So he's now in second place with 217 points. And you can see that where the ISC thought Werewolf would be the hardest task to get a perfect score on, we actually have quite a number of perfect scores on Werewolf so far. So Nicolas Bierkatse, Wataru Inoue, Albert Smith, Marius Trella and Xiandi Ren, and I apologize if I mispronounce any of these names, have a perfect score. What I will do is I will slowly try to scroll down so that you can see exactly what the scores are for your team if you're interested. So I will now show everybody from place 18 up to 41. So take a good look of what you're seeing. Take a good look if your favorite team is there. And we'll scroll slowly farther down. We'll start at 42 now. Ooh, something is changing. It's a live scoreboard, like I said. We still have the live scoreboard going on here. So we go back farther down. And these are still kids that scored 100 points on question 1, or almost 100 points. So this is a good year for question number 1. We're just slowly scrolling down. And I hope you can see your country there. And I will just keep scrolling all the way to the bottom because I know that that is what you want to see. You all want to see all the scores. And I'll just slow down a little bit. And as you can see, we're at place 120 and still many perfect scores for question number 1. So place 120, which is obviously a shared position, is a lot of students that have only scored a full score on question number 1 and have not scored any scores on the other tasks. So, and we'll do this as well. And I've just been told that the official scoreboard is back online as well, which means that, I'll just finish this until we get to the zeros, and then I will not work my way through the zeros. So, it's interesting to see that all of these students are still working, they're still working hard, and at the very top we still have first place USA Benjamin Shi, and then second place from Malaysia Zizong Yeo, and in third place from China Zhenting Zhu. And all the scores in the top 3 are currently unique, which is something that we really enjoy. So that's one of our favorite things. We want a unique ranking. What we're going to be doing is we'll show you the live view from the contest hall again for a little bit while we look up the interviews we've just done in the ISC room. So we've been to the ISC room and we've spoken with 2 of the ISC members, and we have some footage from inside the room, and we'll be showing that to you shortly. So bear with us while we prepare for these interviews. Thank you. Welcome back, and I'm sitting in the hallway right outside the ISC room, and I'm talking to my friend Ali from Iran. Last year we had the IOI in Iran.
Yes.
And then you were in charge of all this.
At that time I was the manager of the host scientific committee.
And how does it feel now that you've done it once?
Very relaxed.
This is very relaxed. Yes. How are things going this year?
Everything is very smooth. So we had a translation night last night, so all the tasks are given to the team leaders, and the team leaders need to identify if there are major or minor objections about the task. The major ones mean that the task to be removed, the minor ones mean slight English improvements in the tasks. So we had no major objections, and we had only one or two major objections for two of the tasks. So they were immediately, very rapidly fixed. And for one of the tasks there were more, but it was very smooth, and the contest today has been also smooth. Yeah.
Yeah. We started a little bit late, but that was not because of the ISC, right? That was not a technical issue.
Yes, the ISC and the HSC main responsibility is to prepare the tasks, the testing material, and all of these have been prepared. I mean the test material since days ago, and the final statements last night.
Right, and so do you know, so I remember that last night the tasks were final at about 12:30, maybe 12:45.
Yes.
And what time did the last country hand in their translations? Do you know that?
You need to ask Tetsushi, because he was in charge of that. The ISC people left when the tasks were final to have more energy for today.
So you were asleep by 1 o'clock?
Not actually.
No?
No.
Did you sleep at all during the IOI in Iran?
That's a really good question. So I remember we were awake even after the GA meeting to prepare the test material, to test it again. I can remember I was awake up to 7, and then I did not.
You did not sleep?
Yes.
No, I remember last year. I remember that very well.
Yeah.
Well, thank you very much for coming out of the room for a little bit.
You're welcome.
And I'm going to go back into the room and I'll just grab someone else, take them out here. We'll talk to them for a little bit, and we'll just show you these little clips as we go along today, just so you know what's going on backstage. Thank you for watching.
Thank you.
Thank you. So let's see. Let's bring up Azerbaijan. Are we ready?
Yeah.
Bring it on. Good morning, everybody. We are still broadcasting to you from the IOI here in Tsukuba, Japan. And with me is my dear friend from Azerbaijan, Farid.
Hello.
Welcome, Farid.
Thank you.
You are on the ISC.
Yeah.
What do you do on the ISC?
Generally or
right
now?
No, in general. What is your role in the ISC?
Okay. We have, as you know, 2 meetings. One in February, one in during the contest. So in the first meeting, we basically analyze the problems, tasks. We select a long list, and then we make a short list from those tasks. And we divide the tasks by the people, between the people in ISC. So I had like 2 tasks to analyze and estimate its difficulty, and then if the task makes to shortlist or not. And currently we are answering the questions, the clarifications, looking at the state of the contest, and so on.
That's a good thing.
Monitoring.
That hasn't been discussed at all yet. So the students can ask questions.
Yeah.
And how many students are using that feature? How many students have been asking questions?
For now,
About approximately
30 or 40 questions. Most of them are like invalid questions, or where the answer to the question is in the description of the task itself. There are questions like, how can I use the WC, the toilet?
the toilets, yes.
Then we say that you should call the staff, etc. And yeah, basically.
So it's a bit of everything.
Yes.
Are there any questions where, when you look at the question, you're like, ooh, maybe the team leader made a wrong translation or made a mistake in the translation?
For now, not yet. Last year there has been such kind of question, if I remember correctly, but this year not yet.
It happens to the best of us. I mean, translations go on until the middle of the night, so it's very easy to make a mistake. And we get newer versions of the English all the time as well. So next year, IOI will be in Azerbaijan.
Yeah.
Are you looking forward to that, or are you a little nervous?
I'm looking forward, and I'm a little bit nervous because it's the first experience for us, and we didn't have any kind of major contests in our country. So we are very much looking for it, and we are already working on it, gathering the team, both on technical side, both on scientific and organizational side. Yeah.
And what will your role be next year?
I'll be the head of HSC and IC at the same time.
So you'll be head of the host scientific committee?
Yes.
Okay.
Host scientific committee, and I'll also interact with the technical side. So basically I'll be the point of contact in the middle between scientific and technical.
Do you still have a job while you're being on the HSC, or is that a full-time position for a year?
No, it's absolutely voluntary.
But it's going to take up a lot of your time.
Sure, and I'm currently instructor at the ADA University in our country. So as this university is a hosting university, so it will be taken into account, and my teaching load will be reduced.
Oh, well, that's good.
Yes, to be able to work.
And what do you teach? What's your background that makes you good at being on an
My
IC?
background is computer science major, and with electrical engineering as minor.
Okay.
Right, so I'm teaching everything you can imagine.
But a lot of algorithm stuff?
Yes, sure. Most theoretical computer science, such as programming languages theory or theory of computation, software engineering, etc.
So if a 15 or 16-year-old kid is watching this show and he thinks, oh, I want to go to Azerbaijan next year, how should I prepare for this? Well, you have to learn how to program.
Yeah.
But which topic do you think he should start off studying?
Okay.
Just name one thing.
Yeah, I like most the dynamic programming
Yeah?
in computer science and algorithms, which is actually very easy to grasp as the beginning, and when you're able to solve problems of dynamic programming style, you get more interested in those tricks, in the magic of programming.
And dynamic programming is where you break down a problem into smaller sub-problems that are basically of the same style, so you just keep solving smaller and smaller things.
Yeah.
Okay, well, so if you're watching this at home and you haven't done anything yet, dynamic programming just to start off with. And with that, I don't think you would score any points here, but it's a start and it will get you interested.
Sure.
And that's important. Well, thank you for watching, and thank you very much for stepping out of the IEC room. I know you guys are busy, and I'm very grateful that you take the time for us.
Yes, thank you for the interview.
Thank you.
See you in Baku.
See you in Baku.
Good afternoon, everybody. It is almost 1 o'clock in this time zone. We are in Tsukuba in Japan, which is located very close to Tokyo. And we are broadcasting to you live from downtown Tsukuba area, where about 50 meters away from us, about 340 students are participating in the International Olympiad in Informatics 2018. This year is a very, very exciting year. We have some cool and exciting tasks, and we have a live scoreboard, and stuff is happening. In first place, and he's been in first place for a while, is Benjamin Xi from the USA with 270 points so far. And you can see the scoreboard behind me. You can also, at any time, go to the website ranking.ioi18.net. So there you can see the live scoreboard. I see my head in the picture. I'm just going to move out of the picture That's how it looks a lot better. So people have been asking me, how are the Dutch kids doing? Well, the Dutch kids are doing okay. There are some kids that have a reasonable score, and 2 of the kids don't have that much of a score. I think most of the viewers, however, are more interested in the Japanese team. Now, if you click in the top left corner of your screen, you can select the country, and then you will see on the left-hand side where what the position is, the relative position of the kids from that specific country that you've selected. Now, Japan, as you can see, has 8 participants. That doesn't mean that they can win 8 medals. We only allow them to win 4 medals. They have 4 official participants and they have 4 kids from their team 2, as we call it. So if you look at the scoreboard, the combo task is the easiest task by far. A lot of kids have scored a perfect score or a near perfect score on that. The task werewolf was expected to be the hardest task by the scientific committee, but it turns out that at this point it seems to be easier to score points on than seeds. And I don't know how where that comes from, but there's a distinct difference there. Now, it's good to see that on seeds there are some 70-point scores, but there are no 100-point scores on seeds so far. Whereas on werewolf, there's quite a number of kids that have scored 100 points there. Now, combo obviously has most kids scoring 100 points, because if we scroll down, you will see student after student scoring 100 points on that combo task. That was obviously the easy task. And then there are a lot of kids scoring 97, which means very close to solving it. Just a few minor things missing. Global scoreboard though, the ranking, that's important. Benjamin Xi in first place with 270 points. Now, let's look at the tasks. In a couple of minutes, we will bring back our friend from Poland, Jacob, who will discuss the solutions to the tasks with us. As I've mentioned, there are 3 tasks at the IOI this year on day 1. The first task is called Combo. And Combo is a task about a computer game. You have a PlayStation-like device with buttons A, B, X, and Y, and you're pushing these buttons to win your game. And there's a secret combination, and if you press that secret combination, you get the maximum score. This is what you want to achieve. Now, what you can do in this game, you can enter a combination of keys, and the system will tell you, you get as feedback, how many in the combination that you've entered, how many points do you score with the whole combination that you've entered. And the scoring is a bit special there. Your secret combination, the first letter does not occur anywhere else in the secret. So, as you know, A, B, X, and Y can be the letters in the combination. If the first letter is an A, then the next letters in the combination, doesn't matter how long it is, will not have the letter A in it. You can enter a combination of up to 8,000 characters and you will get a score back. And the score is basically looking at the secret that only the grading software knows. And they look at the secret and then they look at the longest substring in the secret that they can find in the string that you've sent in. So if the secret starts with an A, and call it ABX or ABXX, and you enter a string that has XXX, ABYYY, then you would be returned a number 2, because AB is a prefix of the secret, and it's the longest prefix that you can actually find in that string. So combo, the easiest task, is about sending in requests where you get a score and then deducting from those scores what the secret combination is. It's a little bit of a code-breaking task. Task number 2 is called Seeds. And the ISC thought that this would be the medium task to get a perfect score on. Seeds is about, you have a rectangular auditorium, call it a gymnasium, with spots, with positions, and every position has a number. So if there are n times m rows and columns, so n times m seats, then the seats would be numbered from 0 up to n times m minus 1. So every number is used. Now, we're calling, so this is a rectangle filled with numbers. And we are going to color all the cells with a number from 0 up to k. We're going to color them black. And now if all the cells that are colored black form a perfect rectangle, so a rectangle with no white holes in it and there are no black spots outside of the rectangle, we call this a beautiful rectangle. And so basically that makes k a beautiful number. Obviously, the number 0, if k is 0, that's always perfect. Because if you only color cell 0, then that's a rectangle and it's a perfect rectangle, so it's beautiful. If you have cell 0 and 1 and they're touching, then 1 is also beautiful. If they're not touching 0 and 1, then 1 is not beautiful, obviously, because the rectangle would not be perfect. And the other rectangle that's always beautiful as well is the whole rectangle. So if you have all the numbers selected, because we said that the number 0 up to n times m minus 1 would be in that rectangle. So if k equals n times m minus 1, you color everything, the whole thing is black, it's a black rectangle, it's beautiful. Now, there is a term that we're now using where, and I'm looking at the thing here, the beauty of a rectangle is the number of beautiful sub-rectangles that you can find in there. So that's the beauty of a rectangle. The question is, you're given a rectangle of numbers, tell me the beauty. So how many numbers k can you find where the result is beautiful? To make it a little more interesting, you will be asked many questions in a row. So you'll be asked you will be given a rectangle, asked how beautiful is the rectangle, so what's the beauty of the whole rectangle, and now two numbers will swap. So you will change the position of two of the numbers. At this point, you have to answer the same question again. So what's the beauty of this new rectangle? Okay, let's swap two more things. What's the beauty now? Swap two more things. What's the beauty now? And sometimes you'll get up to 1,000 questions. It will just keep adding up and up and up. So that's question number 2. Let's look at question number 3. Question number 3 is werewolf. As we all know, werewolves are scary. They change shape. They transform from human to wolf. In this task, the werewolf only transforms once. So the werewolf starts in human form, and at some point in the task he changes into his wolf form. The werewolf has to travel around a network of cities, and the network is connected. So from every city you can reach every other city. Every city has a unique index number from 0 to n minus 1. So there are n cities and they're labeled from 0 up to n minus 1 inclusive. And the index indicates basically the population of the city. So they're sorted by, so the numbers are sorted by population. Now, as you know, werewolves get scared when there are too many people in the city, and humans get scared when cities don't have enough people. So there are cities that you have to avoid. So if the cities are labeled from 0 to n, from 0 up to L, the cities have to be avoided by the humans. So the humans they are not allowed to go into these cities. And from a number r up to n minus 1, the cities have to be avoided by the werewolves. Now you're given two cities, A and B, and the question is, can you make it from A to B, where you start as a human, and at some point in some city you change from human form to wolf form, and then you continue your travels, and then you still make it to city B without being in a city where you're not allowed to be. And so you can only change your form once. If you want to know more details about these tasks, just go online, go to ioi2018.jp, and in the menu, competition tasks, you should be able to find all the tasks, translated into many different languages, so you can find it in many different languages if English is problematic. And just look at it there. You will find a clear description of the actual task with the boundaries and information about test cases and how you have to submit. What we will be doing now is we will go back to the live view from the contest hall, and then we'll wait for our friend Jacob, who should be here any minute now, to discuss the solutions of these tasks. So we'll talk about the strategies and how to solve them, what the proper algorithms are, and what you should keep in mind. So bear with us, just watch the live stream from the contest hall for a little bit, and then we'll be right back. And welcome back to the live stream from IOI 2018. As you can tell by the smile on my face, we're actually having a wonderful time here. It is fun to do this, and we have almost 7,200 people watching this live stream. With me at this point is my friend Jacob from Poland, and we will be discussing the difficulty of the problems and the solutions of them. Now, Jacob, we were discussing the difficulty level earlier today.
Yeah, so, well, it turns that I was right when I said that we're always wrong.
Well, yeah.
Yeah, so apparently the task Werewolf is easier for the contestants than the task Seeds, but, well, we have like more than 10 perfect scores on Werewolf. We have, at this point, no perfect scores for Seeds, only 2 partial scores of 70.
Do you think that the bar chart that we're showing this year, where the kids see how many points are scored for each task, do you think that may have something to do with it? Do you think right now more kids will move to Werewolf because they see their perfect scores? Well, they don't see their perfect scores, but they see that there are more points there than in Seeds?
Yeah, so I think this would have some effect. Actually, maybe I should take back what I said previously. I talked to other ISC members, and actually, if we look back to our notes from the meeting where we were selecting the tasks, it seems like we're already there. Some of us, at least, were expecting Seeds to be harder than the Werewolf.
Okay.
So this time maybe it was just me, not the whole ISC that was wrong. But
so in which order do you want to go through the task? Shall we just start with combo, the easy one?
Let's go this way.
Okay. I have just gone over combo with everybody. And so combo is a task where you have to figure out a secret combination in a computer game where you're entering buttons A, B, X, and Y, and there is a secret combination in there where the first character occurs only one. So the secret combination starts with A, B, X, or Y, but then that letter is no longer used in the rest of the combination, and then it's random combinations of the other 3 buttons. Mm-hmm. And you're pressing buttons, and you get some results from the contest system, and you're trying to figure out what the combination is.
Right.
Tell us some key observations that the students should be making about this.
So, first observation, easy. You can get everything in just 4n trials. By for the first letter, you make 4 trials. You figure out what it is. That's easy, and then you can do the same for all the following letters. Like you can get each letter with 4 questions. This is like the simplest idea one can have. Now, the first important observation is that we can easily get down to relatively easy get down to just 1 question per letter. Mm-hmm. So once we know the first letter, let's say for the first letter we use the 4 or like actually 3 questions.
Right, you use A.
Yeah.
Okay.
And then for each following letter, we can get it with just a single question. And now what happens is that we have already figured out some number of characters. So we know some prefix of the secret word. So the prefix is S. And then let's say the first letter of the whole string is A. So in this case, the combination that we should press, well, it's S.
The prefix that you know for sure?
Yes. Followed by B.
Okay.
And then followed by S again.
Okay.
So basically, okay, let's start with S followed by B. So what we know is that if the next letter is B, then the number of points we'll get is basically length of S plus 1.
Right, increased by 1.
Yeah.
Okay.
Now, if we ask for S followed by B followed by S, actually nothing changes, right?
Because the S, you realize that the first letter of the prefix is unique.
Yeah.
So as soon as you reuse that, it's a reset.
Yeah,
Okay.
basically. So then if we would ask for SB, SX, we would get length of S plus 1 point if the following letter was either B or X.
Right.
Now this alone would not be very useful because we would know whether the following letter is B or X or the other option is Y.
Right.
So we would get some information but not all of it. So what we really need to do to get like all this answer in one question is ask for S, then B, and then S followed by XB,
Okay.
S followed by XY, and then S again followed by XX.
Okay.
So basically it says if the next letter after S is B, we'll get length of S plus 1. And then if the next letter after S is X, then one of the following things we've put would match, and we'd get length plus S of S plus 2 as the answer.
And if you get if nothing changes, then you know it's the third option.
Yes.
Has to be the next
Which
letter.
is Y, yeah.
So this is the clever observation you have to make. So once you've made this, are you there?
Well, you're almost there. This is enough to get like 90 something points.
Okay.
And then this way we would ask something like n plus, let's see, n minus 1 letters except for the first and the last one. Because this doesn't work for like the first or the last letter. Plus 3 questions for the first letter, and then 3 questions for the last one. This gives n plus 4 questions.
So you have to optimize it to get down to n plus 2.
Yes. And then, this is just some, it's a similar reasoning. It's just that in the beginning and at the end, you need to do something slightly different.
You just have to think cleverly about how do I get that first letter in only 2 questions rather than 3.
Yeah.
And the last thing as well.
Yeah.
Okay, and that's doable.
Yes.
You promise.
Yeah.
That's important. That's important. Okay, so that was combo. And I don't see anyone asking questions. So if you have any questions, just seriously, just let us know if you have any questions, because we can see what you type here. We're at 7,350 people right now. You're getting famous. Bring it on. So let's go to, you want to go to werewolf or do you want to go? Okay, let's do werewolf. So werewolf is the medium question today. Although it's, if you look at the scoreboard, it's still very hard because only about little more than 10 people have solved it correctly.
Yeah.
So werewolf is a question where you are there's a person who is a werewolf, and werewolves are either in human shape or in wolf shape. And this specific werewolf has to travel through a network of cities. The network is connected, so from every city you can reach every other city by road. And the cities are numbered from 0 up to n minus 1. And the werewolf starts in human form and at some point has to change and end up in wolf form. And the werewolf is not allowed to reach cities 0 up to L when he is in human form, and is not allowed to be in cities R up to n minus 1 when he's in wolf form. So there are forbidden cities for either shape. There are cities where he can be in either shape, right? And so the question is, can he make it from city A to B with making exactly one change, at some point? So either in A or in B or in any of the other cities along the way. Yeah. Okay, tell us.
All right. So the first thing we need to do is to figure out if we're we're starting in city S, we're in human form. So the cities with numbered from 0 to L are forbidden. So we'd like to know, okay, where can we walk? Now, of course, we can do that by just traversing the graph once, but this would be slow. We have lots of questions to ask. We need to pre-process the graph.
Right.
So that these questions can be...
That's a key observation there that I'd never mentioned. So you will get many questions, and so you'll be given a single graph, but then many questions where L and R, so the boundaries where you're allowed to go, and A and B, the start and end cities, are different. So every question is basically, here's the graph, and now I'm going to ask you 100,000 questions. Is it possible with these L, R, and these A and B? Okay, please continue.
Right. So of course, for each query, we could just have a look on the cities that we can reach, and answer it by using some graph traversal in the linear size of in time that is linear in the size of the graph. But if we want to do it faster, we need to have some smarter approach, and we need to represent the set of cities that we can reach in human form in some compact way. And of course, same for wolf form. So here's the representation. So we're in, okay, let's see which way it is. Let's talk about human form. So the cities with low numbers are disallowed. So we'd like to build a rooted tree as follows. So we put vertex 0 in the root.
Because it's not allowed?
No, just because it's the lowest number.
Okay, yeah.
And then we delete 0 from the graph.
Okay.
Then we have some connected components of what remains, and we build the subtrees of the graph recursively. So for each connected component, we take the maximum, put it in the root, delete it, and then compute the subtrees recursively. Now, you can do that efficiently using union find data structure.
Mm-hmm.
So now, if you look on the tree that you've built, and if you know that you can only use let's say cities numbered from L+1 to N, and if you know your starting city, then we have a look on this where the starting city is in this tree that we've built, and the set of reachable cities is going to be exactly a subtree of this tree.
Okay.
Right. So then, basically, for every starting city and every limit L, we have a single tree that represents the set of cities that we can reach.
And then we do that from the other side as well.
Yeah.
And we just have to see if there's a match.
Yes, exactly.
Is there overlap in between these two trees? Is that hard to calculate?
Overlap, yes. That's another part we need to deal with.
Okay.
So that's step one. Build the two trees.
Okay.
Again, we will need to use union find or like disjoint set data structure. It's called in multiple ways. And then when we have that, the problem basically boils down to we have two rooted trees, and we have questions. Each of the questions specify a subtree. Basically says, okay, here is a vertex. We have a look on this vertex and it's all its subtree. We have also the same question in the other tree. Now, what we need to say is whether the two subtrees have a common element.
Right.
Yeah. And again, for this one, we did this it's part 2 of the solution. So we solve this using another technique. So what happens is that we're gonna traverse the first tree in pre-order order.
Okay.
And then let's imagine the vertices are like lined horizontally.
Okay.
And then we have the other tree that we traverse again in pre-order. And then let's say those vertices are ordered here vertically.
Okay.
So now, every vertex is one in this horizontal sequence, one in the vertical sequence.
Right.
And so now, if we have vertex 3 here and vertex 3 here, we put a point exactly on those coordinates, right? Mm-hmm. So, and when we have that, so we have like a set of points, and then also what we know is that each subtree of the initial trees is actually an interval of those representations.
Right.
So now. All this boils down to is a problem where we have just a set of points on a plane. We have intervals on the x-axis, interval on the y-axis, and we're asking whether there is a point in this rectangle.
Right. Yeah. And there are clever data structures for that.
Yeah. So you have to use sweep line technique and some standard data structures, and you can answer that. The good thing is that all the queries are given to us in advance. So we don't have to, you don't have to use even more advanced data structures that would be able to do that if the queries were given online. you can just pre-process all the answers up front.
Okay, so the key observation in the whole task is...
Oh, there are multiple. This is like the important thing is that you first solve the first piece and then there is a second piece. So you have to do multiple things.
So you start off with figuring out those trees, and then you think, oh, I'm there, and then you're like, oh no, wait, I need a clever way of finding that out. How do I store that? And once you figure that out, you're like, okay, that's sweep line, I can do that.
Yeah. So basically, like, it's first, here is the representation. Okay, here first idea. Then, okay, there are data structures that can compute that. Then I have the trees. I need to do this efficiently. Okay, so here is like a graphical representation. And again, once we have this idea, okay,
right,
there is a data structure that can do that. So
how many lines of code is the model solution?
That's a good question for this one. I'm not sure.
Approximately?
I would guess it's over 100, but
so that's a lot of code to have to get correct.
Well, yeah, it's quite a lot.
Right, and with tricky data structures that you're working with.
Yeah, I mean, it's possible. I haven't seen the shortest possible. So some people can do those things in surprisingly few lines.
Hey, we see the scoreboard, so we know that they can do them very fast. Okay, cool. So this is what you thought would be the hardest, but some of the IC people were like, this is not trivial, but there will be kids that will score this very easily. Okay, well then we'll move on to the next question. And the next question is seats. This is about the rectangle that has beautiful sub-rectangles, and we're trying to find the beauty of the big rectangle, which is the number of beautiful sub-rectangles in it, where we define, I like your explanation very much, where we say a sub-rectangle is beautiful if for the number, is you pick a number k, and you color the cells 0 up to k, color them black, and if those cells form a perfect rectangle, so when you look at it, it's perfectly black with no white spots, and there's no black spots outside, then it's beautiful.
Yeah, you can also say that a rectangle is beautiful if the rectangle of size, let's say t cells is beautiful if the numbers in it are exactly 0 to t minus 1. Yeah.
Right.
Yeah, so there's the same thing.
Yes. And so we're given a rectangle, we're asked how many beautiful sub-rectangles are there, where it's obvious that the number 0 is always beautiful, and the whole rectangle is also always beautiful. And so a border case is the rectangle with only one seat, because that doesn't have two beautiful sub-rectangles, it just has one. And the question is not just calculate this, but the question is, calculate this many times where between each calculation, we just swap two numbers. Right?
Yeah.
Okay, what's the key observation to start this solution with?
So actually this task is really nice in terms of solution, because there is a key observation that does lots of, that basically when you get it, you're more than halfway there.
Okay.
But it's also very tricky.
Okay.
So here is the observation. So we have the rectangle. Let's have a look on all subsquares of size 2 by 2, or like sub-rectangles. Now, let's say we have, we've picked K, we've painted everything up to K black, the rest is white. So now, let's say somebody, just takes a picture of all 2 by 2 sub-rectangles, and then shows me just the pictures. I don't know where those come from. I only know, there will be some that have 4 whites, there will be some having 4 blacks, there would be also some other of the, possible 16 combinations, right?
Right.
And the key observation is that just by looking at what is the number of all those 16 combinations, or of each of them, I can figure out whether the initial picture shows a single rectangle.
You can only have one upper left corner of the rectangle, and only one bottom right corner, and so that's the key observation. And then if you have so many on the right side, then you need to have the same number on the left side, and bottom and top the same way.
Yeah, exactly. And then there are some forbidden combinations, like 3 black and 1 white. It's like a non-corner.
Right.
Like a reverse
corner.
Yeah. So those we cannot have.
Okay.
Actually, it's even simpler. So you can say that we must have exactly 4. Let's see. If the pictures come from like a valid cell, I mean, it is not that somebody just brought me a set of random pictures. If they really come from an existing cell, which will be we can assume. This initial picture represents a single rectangle.
Yeah.
If what I got is exactly 4 2x2 squares with exactly 1 black, and there are no 2x2 subrectangles that have 3 blacks.
Okay.
So just these 2 simple conditions, if they are satisfied, I know the initial thing is a rectangle.
Okay.
All right. So this is the super important information, which basically we now reduce the problem a lot, right?
Right.
All we need to take care of is like very local. So if something changes in particular, I only need to update like just
2 things.
Just a bunch of few more, but if this number changes, I need to update all the 2x2s that contain it.
Okay.
Yeah, but not much in any case. So now once we have that, let's fix one 2x2 subrectangle. I mean, this observation allows you to solve the problem very easily for the a fixed parameter of k and just a fixed cell, right? Right. So let me think. What is the best? I mean, we now can. Let me think whether it's better to consider multiple case first or changes first. Probably. Let's see. Well, let's think about different case.
Okay.
So take a look on one 2x2 subrectangle. It has 4 numbers, right?
Right.
So the way it's painted white and black obviously depends on k.
Right.
But if k goes from 0 to size of the cell -1, the colors in this cell would only change 4 times.
Right.
Initially it's all white, and then I'm going to get 1 black, second black, third
black,
and then
fourth black. Yes.
So basically, it's convenient to think about is that this 2x2 subrectangle would basically provide 4 pieces of information. Like on this interval of numbers, this is who I am, and then on the following interval, my appearance is like this, right?
Yes.
So it's very compact, and it tells what this subrectangle looks like for different values.
There are 4 changes.
Yeah.
So there are 5 intervals.
Yes.
4 changes. Okay.
So now, well, I'm going to use the magic word again. So now we can take all of this information aggregated from all the 2x2 subrectangles, put them in a data structure that would aggregate, the types of different subrectangles at different points in time, or like different values of k.
Right.
And then again we need to use segment tree with lazy propagation. And then when we use that, we can actually both say what is the number of beautiful subrectangles in the initial cells, and also update this efficiently.
Right.
I mean, I don't want to go into details here, because if you know segment tree with lazy propagation, you probably can work out the details yourself. And then if not, then I would recommend our audience to read about the data structure first.
Mean, if you don't know about the segment tree, but then you haven't been paying attention for the past 3 years or 4 years, because we've had segment trees or a variant of segment trees every year.
So this one is actually quite tricky, because this one is a tricky variant of a segment tree, because I believe the operations we have to support is add or remove 1 on this interval, and then count the number of elements that are, I think, equal to 4, something like that.
Okay.
So this is something maybe a bit non-standard, but some slightly more advanced version of segment tree would be able to do that.
It's a cool task.
Yeah,
it's a clever task. And it's an interesting observation that the kids have to make. And if you look at the scoreboard, there aren't too many kids that have probably made that observation. Because if I sort the scoreboard by the score of seats, there's only 2 kids that scored 70 points. 150 and everyone else is 37 or probably less than that.
Yeah, so the third subtask, the next to last subtask, is when this whole rectangle has height 1.
Right.
And we believe this would be a hint. Because now if we look on this case, it all becomes simpler, because the forbidden, well, we don't have any 2x2 subrectangles anymore. We only have like,
You want to have one change from white to black and one change from black to white.
Yeah.
And anything else you don't care about.
Yes,
Because
exactly.
if you're like that, everything is going to be perfect.
Yeah, that's right. So then, we believe this may be a hint that would help contestants, get to the full score, but looks like they're still working on that.
I think the observation that we're making here is a tough observation to make.
Yeah, oh, sure
I mean,
it is.
it's in hindsight, it's obvious, but when you're thinking about it, what do I have to store? And that's what IOI is about, right? How do I don't store more than I need to store?
Yeah.
And store it in a way that I can access it the fastest, smartest way possible.
But it's also surprising, right? I mean, imagine you have a gigantic rectangle painted on, there is a gigantic field which has some white and black cells. You have people standing on it. Everybody just says what they see around themselves. And then, if you get this information, you can actually say whether this whole big picture is a rectangle or not.
Right.
I mean, this is counterintuitive.
No, but I think if you phrase it like that, you're already. I mean, you're phrasing it in the, in a way of the key observation, right? If you're phrasing it like, this would be the big hint, right? If the question were phrased as, they're standing there, and you get the information, tell us, is there one rectangle in there?
Yeah.
If that were question, sub A, then many people would be making that key observation.
Oh, yeah.
Right? Because this is the key observation. You're just asking them the key observation.
Yeah. But what I mean also is that, to me, it feels counterintuitive that it's even possible. So it's, I guess the contestants are not even trying to think that way.
Right. Yeah, I see that. Okay. So we have almost a little more than an hour left. And if you look at the scores so far, is this going the way you guys were hoping it would go?
I think we have a nice distribution of scores, which is good. At some point, we had like a huge tie of contestants having 100 points.
We still have that, I think.
Yeah. I mean, it's also important where this tie is. So at some point, the regulations say, I believe, that the number of contestants who receive medals is at most the half of all contestants.
Yes, so you don't want to have the tie there.
So if we have like a 90-way tie, including the bronze medal cutoff, we may, in theory, get like 90 medals less than we would have otherwise. Of course, this is not going to stay like this, but...
Right. I mean, and there's still day 2.
Of course.
And there's still an hour left to go. And so looking at the scoreboard, we currently still have Benjamin Xi from the USA in first place with 270 points. And he is working very hard on making this key observation for seeds, because he has 70 points for seeds. And there's Jianglong Chen from China, 231, with his buddy Quandi Ren, also from China, 231 points. And then a bunch of other scores. We don't have that many kids scoring more than 200 points. So if you have more than 200 points, that's position 14. You're very high up on the scoreboard. At this point, for the viewers at home, and I don't know if you know this, but Jacob already mentioned it, half of the students get no medal, which means half of the students do get a medal. And these medals are distributed approximately in the ratio 1 to 2 to 3. So out of that half of that half, so a quarter get a bronze medal, 1/12 gets gold, and the rest in the middle gets silver. Here it gets too complicated with the fractions for me.
Like 1/12 of all contestants get gold medals.
Yes.
And then twice of that was 1/6 get silver, and then one. Okay.
And then
I get confused as well.
Well, then a quarter,
quarter gets bronze. Yeah.
Yes, and then and the bottom gets nothing. We don't have distinctions. We don't have anything like that. So that's the scoring system. If you're watching the live scoreboard as well, so at what was that? Ranking.ioi18.net. If you're there, and we have the link also up above the video. If you're watching watching that. On the left-hand side of the scoreboard, you will see you see a chart that tells you how many points people have scored, and the left side has some tick marks at the quarter point and the halfway point and three-quarter point, but the right side has check marks at approximately the boundaries for gold, silver, and bronze. And remember, those boundaries may change slightly depending on tie. So this is just a fixed scoreboard with fixed tick marks there, but it's still interesting to see that. What we'll be doing is we'll go back to the contest hall and show you what's going on there, because it's getting very, very exciting there. And we'll be back in a little bit with more information from right here. So let's go back to the contest hall. Good afternoon, everybody. If you have been watching, you are still looking at the IOI live broadcast from the International Olympiad in Informatics in Japan this year. We are in the wonderful part of Japan called Tsukuba. And it's pretty here, and it's even prettier because we have just received the first perfect score of the day. Benjamin Shi from the United States of America has just solved the problem seed. This was the hardest problem so far to solve. He has 100 points on that, so now his total score is 300 points. His day is finished. He still has a second day to go through, but if you look at the results, isn't it exciting that we so far have only a single perfect score, and then a bunch of unique scores below that. And I know that at this point, the viewers from Europe are probably starting to tune in. The ones in the US are tuning out, but your guy is in charge right now. So if you're from Europe, today at the IOI, this is day one of the competition. We have approximately 340 students participating in the hall right next to here. And they are working on 3 tasks. These are 3 very, very hard questions to work on. They're tasks of an algorithmic nature. And let me just quickly walk you through the 3 tasks. If you go online and you go to ioi2018.jp, you can click on the link and download the tasks yourself. And if you go to ranking.ioi18.net, you can see the live scoreboard as well. So all these things are up live and running. And we have laptops around us, and we're just in this little room. You see the laptops. We see the animal looking after us here. And we're just sitting here. I have all the information here, but I'm going to go on this screen to the different tasks. Task 1 of today, this is the easy task, and this is already ridiculously hard, but the easy task is a task called Combo. In Combo, you're basically playing a game on your PlayStation, and you have 4 buttons, X, Y, A, and B, and with these buttons you can make combinations, a combo for a better attack. And there are special combos that get you more points. Now, in this task, there is one combination that's the secret combination, and you're trying to figure out what the secret combo is. So it's a little bit of a code-breaking thing. Now, how do you do that? There's a secret combination that consists of n characters, so n letters for X, Y, A, or B, and the first character never occurs again in the rest of the combination. So if the first character is an A, then you know that the remaining n-1 characters will not have the letter A in it. Or for the B, vice versa, it's the same system. Now, if you know what a prefix is and what a substring is, life gets very easy. But let me quickly tell you what a prefix is. If we have a combination, a prefix is a set of letters that starts at the beginning and it's just consecutive letters and there's nothing missing there. So if the string is ABC, a prefix of ABC would be an empty string, or just the letter A, or AB, or even ABC, the whole string. C is not a prefix, and BC also not, and AC is not even the substring of this, but A or A, B, or ABC are all prefixes. Now, how do you get to figure out this combination? You send in a combo of yourself that can be a maximum of 8,000 characters. So even though you know the combo is only n characters, you can send in a set of characters that's much more than that. And the system will tell you in your string that you've submitted, is there a substring, so a set of characters one after each other, so a consecutive substring, that's a prefix of the secret combination. And if there is, and if there's multiple, we look at the longest prefix that you can find in the string that you've submitted, and the only feedback you get is how long is that prefix? So how many of these things occur in there? Now, when solving this problem, step one is to figure out the first letter. And so that's, let's for now just assume it's trivial, that you can do it in 3 questions. You can do it in 2 if you think about it. But if I ask question, if I send an A and the answer is 1, then I know that A is the starting symbol. If the answer is 0, I know it's not A. Then I start in a B. And so after 3 questions, if I receive a 1 in there, I know that that's the start symbol. If I don't receive a 1, then I know that 1 that I haven't asked is the starting symbol. And the starting symbol is already a prefix. Now, once I know the prefix, it's just up to me to figure out what the next character is going to be. So I want to keep extending that prefix by 1 character. With every question that I ask, I'm trying to add a single character. And that's actually reasonably easy to do, because if S is the prefix that I already know, I can ask SA, that's a new letter, assuming that A is not the starting symbol, then another S, and then I know that if the answer I get is 1 more than the length of S, then I know that A is the next character. If I don't get 1 more here, so I have to ask a different question, because it could still be X or Y, presuming that B is the starting character. So I would ask SA, S, B, so not B, S, X, Y, or XA, to figure out what the next symbol is. And if you think about this, you can figure out a reasonably easy way of doing this. So where every question you ask, you can extend your prefix by 1 single character, and then it's just a matter of asking questions. With that observation, you score almost 100 points. If you want to score the full score, you have to think more clever about the first 2 questions. So the way you're going to find out the first character of your of the secret code, because like we said, you can do it in 3 questions trivially, but you can do it in 2 as well if you think a bit cleverly about how to combine things. Create 2 special strings to start off with. And the same actually goes for the final character of the secret code as well. So if you're able to optimize that just a tiny little bit, then you're there. So that's combo. That's the easy task. Many students have a perfect score in this task. Task number 2 of today is the task, now I have to go to my screen, it's called Seeds. And the Seeds task is a task where I have a rectangular grid filled with numbers. And so if the grid has n cells in them, then it's filled with the numbers 0 up to n minus 1. So only unique numbers are in that grid. Now, the question is, if given a number k, so any number in that range, and I paint all those squares black, do these squares form a rectangle of exactly k cells that only, so I'm picking a rectangle, a subrectangle of k cells, and if that subrectangle has exactly the numbers 0 up to k in it, or 0 up to k minus 1, then I call this a beautiful subrectangle. Well, the question is a little bit harder than this. The question is, you're given a big rectangle, and how many beautiful subrectangles can you find inside this rectangle? Now, obviously, the rectangle that only has a single number in it, so the subrectangle with just a 0 is beautiful because that by itself is square. And the whole rectangle is obviously beautiful as well because it has all those numbers in there. But how many subrectangles can you find that have the numbers 0 up to a specific number and then they have exactly that number of cells? So this is the question. Now we're going to make it one little bit harder. And instead of asking you this question once, we're going to be asking this question many, many, many times in a row. But not the same question, obviously. We give you the rectangle. We ask you, how many beautiful subrectangles are there? And we call that the beauty. So what's the beauty of the rectangle? Then we'll swap two numbers. Exactly two numbers will swap place. And then we'll ask the same question again. And then we'll swap two numbers. We'll ask the question again. Now, we've just been discussing with Jacob from Poland, Kuba as he liked to be called, and we've just been discussing a key observation you can make here. And if you don't want to hear our key observation, cover up your ears, or if you need a little more of a hint, look at the third subtask that should give you some information. That should be a little bit of a hint towards making this. But basically, if you look at all the individual cells and you look at what they see around them, if you were to get that information from every cell in the system, you would already be able to tell how many, if it's colored or not colored. You would be able to see if it's a perfect subrectangle. So basically, we're coloring the cells up to K black and everything else white. And in order to do that, and in order for that to be a perfect subrectangle, you would know that that subrectangle needs to have one upper left corner and one upper right corner and one lower left and one lower right corner. So you don't need to look at everything. You just need to count how many of those special corners there are. Or, in this case, if you would divide up the whole grid into groups of 2 by 2 cells, then you would just look at every set of 2 by 2 cells, all these 4 cells, and they only have a specific number of black and white cells that can be in there. You would look at all these and you would count these, and you would see that if there's one 2 by 2 square that looks like an upper left corner, we're okay. We might be okay. But if there's 2 that have that shape, then you're definitely not okay. So this is a key observation to make, and the third subtask has all the squares lined up in a row. So the rectangle has height 1, so they're all lined up in a row, and in order for there to be a perfect subrectangle, you basically need to have a subset that has those numbers 0 through K in there, which means you have one change from white to black and one change from black to white. Those are the only things you have to keep track of there. And that's apparently a reasonably solvable subtask for this problem. So this is seats. Seats is by far today, if we look at the scoreboard, the hardest problem. The third problem that was thought to be the hardest by some people on the ISC, because it has some tricky data structures in it, is werewolf. In werewolf, we have n cities, and the cities are labeled from 0 to n-1. And the index number of a city is basically an indication of how many people live in that city. You are a werewolf, and a werewolf, as you know, has 2 shapes, a human form or wolf. This specific werewolf starts in a city A as a human, and he wants to travel to city B and end up there in wolf shape, in wolf form. So he has to make exactly one transformation somewhere along the way. And the transformation happens inside the city. Well, so far so good. What makes this hard is that as a werewolf, you try to avoid the very populated cities. So if the cities are labeled from 0 to n-1, in ascending order of population, a werewolf is never allowed to be in any of those top cities. And we call this, there's a boundary R, so the werewolf is not allowed to be in any city with index R or higher. the wolf is, sorry, that's the wolf. The human doesn't like cities with few people. And so we have another boundary, L, and the human is not allowed to be in any city with L or fewer inhabitants. So those are the two boundaries. So somewhere along the way, the human has to start in a city where he is allowed to be human, go to a city where he is allowed to be either human or wolf, and then end up in the city where he is allowed to be wolf. So he could still be allowed to be human there, but this is what's happening. And the question here is, how do you solve this? How do you figure this out? This was thought to be very, very hard, but it turns out that a lot of kids have managed to do this properly. Now, before we go on, here as well, let me just, you are given one set of cities that is connected, and then you're asked many, many questions, where each question is of the form, well, what if L is this and R is that, and you start in A and you want to go to B? Is it possible? Okay, how about this L, R, A, and B? So you still have the same grid of cities, the same network, and you're just asked question after question after question. You're trying to solve this as quickly as you can. Now, key observation here is that you can create a tree-like data structure of the cities you can reach in one shape and the cities you can reach in another shape. And you just have to find out if there is a match there. What I'm going to do now is I see my dear friend Richard Peng come in, and we're actually going to talk to someone else. So we'll go for 1 minute to the live broadcast of the contest hall, and then we'll bring in our next guest, Richard Peng, who is Canadian, right? Woohoo! Bring him in, let's go to the contest hall. Welcome back to the live broadcast of IOI 2018, here live from Tsukuba in Japan. The contest has been going for 4.5 hours. We have one kid that is finished, and everyone else is still hard at work. With me, I have my dear friend Richard Peng from Canada. Welcome. And you're on the show every year.
I wasn't here. I think I wasn't here last year.
Yeah, every year we bring you out and we talk about questions.
And last year the hard disk crashed while I was on the screen.
Yeah, wasn't that great?
What are you going to do to me this time?
Nothing. You don't have a laptop with you this time, so nothing can go wrong. And the typhoon doesn't hit until Wednesday, so everything should be fine.
Well, we'll see.
Okay.
We'll keep my finger crossed.
Fingers crossed. So you have only 10 minutes because the final 15 minutes is always the hardest part. I mean, it's already starting to heat up, right?
Well, this year the host they were really careful with planning their server load. So judging load-wise, we haven't seen any slowdowns yet.
No? So when a kid submits a problem, how long will it take on average now for the kid to get a solution, to get his score for that submission?
So have you explained how the judging mechanism is working?
So what we've discussed is that, and we may have new viewers now, because we have almost 9,000 viewers.
Whoa.
This is because of you. I've been telling them you would come on. And so we've discussed that they submit, it goes to a distribution server that's located somewhere in Tokyo, that then sends it back to all the worker servers here. And then it, depending on how busy the worker servers are, it will just grade everything in parallel. So every subtask will go to a different worker server.
Not just every subtask, every test case.
Every test case goes to a different worker server.
Every file so when a program gets submitted, for example, on Werewolf, it's ran on about 120 test cases. And this gets distributed to all the machines. Mm-hmm. So there are 80 grading machines. So each grading machine gets about 1 or 2 of these test cases, and then the results are once again aggregated afterwards.
So he gets basically, it's almost instant response. If nobody else is responding, you can get your result in 5 seconds.
So today, aside from a brief network outage at about 30 minutes into the contest, the response has more or less been instantaneous.
Well, perfect. Are the kids loving it?
Well, I mean, I haven't had a chance to talk with the contestants, right? They're still working hard in the contest hall. But I imagine this is like, as someone who has done contests, just being on the receiving end of this, in my own experience, this has been, it's always very fun to have instantaneous response on everything you're trying.
Right. Was the network outage, was that just something accidental here, or something set up, or did someone trip over a cable?
So I can tell you that I tripped over 2 cables on the way coming here.
Well, the whole building has been wired for us, right? I was told that the day before they set it up, it was a badminton court, the contest hall,
Wow.
and now there's wires everywhere.
That is, I didn't know what it was before, but I understand that
Yeah.
it's a gymnasium with
Yes.
a lot of spectator area and all that.
So you are the head of the ISC.
This year I'm the ISC chair.
You're the big boss. So you've seen all the questions.
We selected the questions in February.
Right.
We chose them. We chose the competition tasks as well as the backup tasks, which are in case there's some issue with the preparation of one of the tasks that's currently slated for the competition.
And are you extremely happy with the tasks? If you
Well,
look at
I
the
mean, we have
scoreboard, right? I
only-
mean, you judge by the scoreboard. So right now there's one perfect score.
We were hoping for today, we were hoping for a score distribution that is a bit higher than this, but not much higher.
Okay. Well, I mean, the bulk of the kids that scored 100 points, that's now getting a bit down because these kids are scoring something else. We had a big load of children scoring 100 points on the first task.
Has anyone described combo to you as button mashing so far?
Everyone has described it to me as, you just take your PlayStation and you bang on the buttons and you're there. So you have a different description here.
Oh, that is colloquially referred to as button mashing.
Okay.
So yeah, it's the same idea. You take
Yes.
your PlayStation and just press
Yeah,
all the
ding,
buttons.
ding, 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 ding. Right. So we've done combo, and we've discussed how once you have a prefix that you know, that you can extend it by 1 with every question, and that the only 2 problems that you have then are coming up with the way to find the starting character in less than 3 questions, because 3 questions is trivial. And that the final question is also hard, finding the final character.
Yeah, the final one you need 1 extra question to find the final one.
Right. So how do we do the first one in only a single, in only 2 questions? What's the key observation there to go from 3 questions for the first character to 2 questions?
Well, it's just a little more casework essentially. So let me recap what the finding 3 questions, finding the first character in 3 questions step looks like. So I mean, the problem is you can ask for a string and it tells you how many characters in the string. Well, what's the longest part of the string? That's a prefix of what you have. In terms of finding 1 character, what is really, if you want to get just the first character, you can just think about it as, is a character in my string is a character in my string the correct first character? So you can simplify this a little bit. And the way to get 3 questions is you just press A. It says yes or no. If it says yes, I mean you're done.
Right.
You press B. It says yes, you're done. So it
Right.
says no. And you press X, same thing.
Right.
And to observe it, you don't need 4 questions. You need only 3 questions. What you do is to notice that after you press A, B, and X, you get no. The first character must be Y.
Right. So that's the 3 questions. Yes.
That's 3 questions. So to reduce this by 1 question, what you do is you say, what if I just press both A and B at the same time?
Okay.
I just press A, B together.
So you can get 0, then you know it's X or Y.
If you get 0, you know it's X or Y, in which case you can press X.
If you get 2,
So if you can't get 2.
you could.
Oh, you can get 2 if the string starts with A, B.
Right. So you could get 2, but that just gives you this substring of AB to start with.
If you get 2, you know that it must be AB. If you get 2, it's actually a lucky day,
Right.
Because you get the first 2 characters
Right.
correctly now. And if you get 1, there's 2 possibilities. It could either be A, it could be AX, could be your correct string. In which case, I mean, AB, right? The longest common prefix is AB and AX. That's A.
Right.
Or it could start with B.
Right.
now you have two choices, and you have one question left to do. What do? You know the answer is either A or B, and you have one question.
So you just ask one of them.
You just ask A.
Right.
And then it basically becomes the same situation.
And those are the two observations that you just need to get the perfect score.
Yeah, the perfect score, you can actually get a slightly below n as n gets really big as well. So you can actually take this kind of stuff and can do a little more to it as well. So the thing to notice is that it is potentially possible to say that if say my length of my secret pattern is say 100, what you can do is you can guess a lot of these 4-character combinations. So right now there is this thing where you guess 2-character combinations.
Right.
You can do this to 3-character, 4-character, and so
right, because you can guess 8,000 in one go.
And every go you have a fairly long string you can guess. So you can, after you determine the first character, you can actually pack a lot more things. So if what you have so far is fairly short, you can actually pack a lot more in there as well.
Right. And so that is key to getting a perfect score here, or not?
That's not required that's not required for perfect score. So perfect score right now is that if the length of my secret string is n, and you use something like n plus 2 guesses.
Right.
This kind of stuff is for getting below n. You can actually do a little better than what's required for the perfect score as well.
Right. And why did you choose that? Why did you, as the ISC, why did you decide that you wouldn't ask, you wouldn't want them to go even beyond for the perfect score?
That's a very good question. And that actually has a lot to do with the way we judge these tasks. So the way that we judge these tasks is that we say that your goal is to write a program such that for every input, it does pretty well. The problem with this kind of extra gain is that this only kicks in when your secret string is very long.
Okay.
So if your secret string is, say, length 1 or 2, you still need this many guesses. For example, if your secret string has length 1, I think by what we just talked about, you really need 4 guesses. You really need 2 guesses.
Right.
And you can actually prove that you need 2 guesses. So it's very hard to set up, to explain as a specification, is that only on the long answers you're supposed to do better. So the difficult part of this problem in terms of getting less than n is actually for the really short answers.
Right. Okay. And you expected this to be the easy problem of the day?
We expected combo to be the easy problem.
It's also the easiest one to explain. I mean, we don't need a whiteboard. We don't need anything to explain this task.
It's as much of a button mashing or Xbox, just press every button.
It's just your PlayStation. You try it all out. And so are you looking at the programs that the kids are submitting as the ISC?
So I can tell you that for the second 2 problems, both Seeds and Werewolf, the first correct solution was there was just a giant round of applause in the ISC room.
Oh, seriously?
Yes.
Yeah.
There's a lot of excitement the first few solutions we see that get full scores.
Are there any people that come up with algorithms that are different or more clever than what you came up with?
So quite a few of the solutions submitted on Werewolf there were quite a few clever ideas in them. Some of them are fairly different than what we were thinking. Some of them are a lot more significantly simpler.
Okay.
So a lot of it, what it became is that for the problem Werewolf, what it kind of boils down to is it boils down to manipulating trees.
Right.
Manipulating 2 trees simultaneously. And here there was a lot of fairly clever things that one could do. And this is also a situation where if you know a few less tools, you actually come up with something that is more clever because you're forced to use the less high-powered tools.
Right, you have to come up with something yourself.
You have to come up with something yourself instead of just, there are very high-powered tools to deal with a problem, like once you bring to the tree version.
Okay, cool. So your workers are not really hard at work right now? You're 70 or 80. How many did you have? 80 workers?
Kim, you're going to just jinx it again, aren't you?
I am. And I'm just, we're at 300 points. We only have 15 minutes left to go. So I just want to know.
Can I tell you in 25 minutes? And I would rather go watch the workers at this point.
Oh, seriously? You don't have that on your phone? Because last year, I remember, who was in the TV show last year? We had someone in that on the phone was watching the status of the workers. And then when stuff went down, he just jumped up and ran out.
I think I was looking at the scoreboard. And the scoreboard, all of a sudden, the timer increased.
Oh, increased by half. I remember that.
You're just gonna jinx it again.
I will not jinx it. I'm sorry. We will just, knock on wood, will not jinx it. We only have 15 minutes left. It's been going perfect so far. We started 40 minutes late, but that was not because of the ISC. That was just taking the kids into the room took longer than expected, right?
I'm actually not sure. I mean, we're gonna have our postmortem when these things.
No, because we were making movies at downstairs at the time when the contest was supposed to start, and the kids were still coming in. They were lined up outside and just checking their badges and making sure they did not bring any illegal stuff with them. Was taking a lot of time. So that was just that was the thing there, the key takeaway to take home. Okay, well, thank you very much for your explanation, and thank you very much for coming on to the live broadcast. And so the number has gone up again, the number of viewers. See, it helps when you're in the show. It really does. And
I'm
so
still amazed that you have a 4-digit view count, Kim.
this every year. This is people like this, and Europe is currently waking up. So the people in Europe, if you've just joined us, this is Richard Peng from Canada. He is the chair of the International Scientific Committee. He is the main person responsible for the quality of the tasks. And I know he does it with his team, but you're the chair. If something goes wrong, you get the blame. And if everything goes right, nobody cares about you. Everybody's going to thank the whole ISC. That's how it works.
You're just jinxing things even more, aren't you?
And so we are very, very happy with having him here on the show. It's a perfect day so far. We have one perfect score at this point. We have a scoreboard that's down again, but we'll fix that soon. So all should be well. Let's go to the live view from the contest hall. Good afternoon, everybody, and to the viewers in Europe, good morning. This is IOI. We are broadcasting to you live from Tsukuba in Japan, and I still don't know how to pronounce it, but everybody behind the cameras is now laughing, like, yep, he has no clue. But anyone looking it up or having to type it into Google, Tsukuba. And we are in the final minutes of the first competition day. Today has been a very exciting day. We started about 40 minutes late, but that had no technical reasons as far as we could determine. So everything we've heard from a technical point of view, there have been no issues whatsoever. And previously I had my friend Richard Peng, who's the chair of the ISC, the International Scientific Committee, on here. And he kept telling me, don't give too much praise because you're jinxing it. But I mean, it has been a marvelous day. We've had 3 excellent tasks. And so far, as I can see, we only have a single perfect score, and every once in a while, just to be sure, I press refresh, even though I know the thing automatically refreshes. If you've just joined us, on the top of the screen, there's a big button that says Live Scoreboard. And if you click on the Live Scoreboard link, you'll be taken to, you guess it, the Live Scoreboard. You'll see 3 tasks there listed. So the first task is combo, second task is seeds, and the third task is called werewolf. The difficulty level of these tasks is, it actually turns out to be combo is the easiest one, then comes werewolf, and the hardest task so far is seeds. We only have a single perfect score on seeds, and it doesn't get much better is what I always say. So if I sort by the scores for seeds, you see 100 points, 70 points, 50 points, and then a bunch of 37. So really, really hard task. Whereas if we look at werewolf, we see a lot of 100 points. If we look at combo, we see many, many perfect scores. But that's the whole goal of today, is to have a distinction in the top, and besides the top, make sure everybody scores some points. The 3 tasks today, if you look at the task combo is a task where you're, banging on your PlayStation, and it has 4 buttons, X, Y, A, and B. And by banging on the buttons, you X, 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 Y, 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 A, B, B, A, Y, X, Y, you enter a combination of keys. Now, the computer knows a secret combination, and your task is to find the secret combination in as few guesses as possible. So a guess is just you press a bunch of keys and then you say, this is my guess. That's one guess. And then you get some answers back. And if you want to know the full details of this task, then just go online to ioi2018.jp and download the tasks there. Task seeds is reasonably hard to explain and extremely hard to solve, and impossible almost to solve perfectly. This is a task about a rectangular grid that's filled with numbers. If the grid has m places in it, m squares in it, then it uses the number 0 up to m minus 1. And you're trying to color all the cells from 0 up to k. And if these cells that you colored form a rectangle of exactly, a k plus 1 cells, but if it forms an exact rectangle, so you color these cells with 0 up to k, and if everything that's now black is a rectangle with no white holes and there are no black spickles around it, then you have found what we call a beautiful subrectangle. Now, your whole grid has a beauty score, and the beauty score is basically the number of beautiful subrectangles inside of it. And you're trying to figure out what is the beauty score of a grid that you're given. It gets a little bit harder. You're given the grid, you ask for the beauty score, and now we swap two numbers. And then we ask you the same question again. And we swap two numbers. We ask you the same question again. So we keep doing this for many, many times, just to make it a little hard on you. So the trick is not just to find the answer, but also to find a clever data structure where you can store the state of the grid in a way so that it's easy to make changes in some spots of the grid without having to recalculate the whole grid again. And there are some key observations that can be made, and if you've been with us for a long time, you will have seen the key observations. If you haven't, if you look at subtask number 3, where the height of the grid is always exactly a single cell, and if you think about that carefully enough, that may give you a hint towards the key observation for the big grid. So that would be the thing to do right now, and otherwise just look at the official solutions on the website that will show up later. The third task, werewolf, is a task about werewolves, you guessed it, who take two shapes, wolf or man. If a werewolf is in a human state, he can change over only once in this task to the wolf state. The werewolf travels around a network of cities, and the cities are connected by roads. There are n cities labeled from 0 to n minus 1, and the index number of a city basically indicates the population in that city. So a higher number means more people are in that city. A lower number means fewer people in that city. Now, as you know, werewolves are scared of people. So when the person is in his werewolf shape, in his wolf shape, he should not be in any city that has a lot of people in it. And there's a threshold there, and we're calling that R. So any city with an index number R or higher, R or above, the wolf shape should never be in there. He's not allowed to be there. And humans are afraid to be in cities with not too many people because bad things may happen there. And we have a threshold, a lower threshold called L. So in the human shape, you're not allowed to be in any city with an index of L or lower. Now the question is as follows. You're given the network of roads, you're given L and R, and now you're asked, is it possible to travel from A to B according to the rule that you're never in a city where you're not supposed to be in, and you make a single transformation from human to wolf. So you start as a human, in a city you change from human to wolf, and at the end you're in your city B in the shape of a wolf. The timer on my screen says there's only 5 seconds left, and so I have other people looking at the scene from the hole, and as soon as we see people getting up in the hole, we'll actually transfer to the hole so you can see what's happening there. So today has been an exciting day. So far, what is happening? I see the clock now, the current time. So I guess people are getting up. So far it's been very exciting. I see only a single perfect score. I see, smiling faces all around me, which is good. And everybody is very happy. We'll have another day. So competition day 2 will happen shortly, and that's in 2 days. And At that point, we will be back here. We'll discuss the questions from day 2 with you. We'll discuss the solutions again. We'll look back on day 1 a little bit. And hopefully we can bring in some guests from some of the teams, because I do know that the parents are asking for the guides. They want to see who the people are that are looking after their students. I've just been informed that the camera in the contest hall is currently dead, and we're trying to fix it now. So I'll just keep talking for a few more minutes to see if we can get it fixed, and otherwise, it's just going to be this for today. So tomorrow we're trying, or in 2 days, we're trying to bring in as many guides as we can, so one by one, just so you can see how nice and friendly the people are that we are hanging out with here and that are looking after your students. The organization here has been fantastic. The 350 students in the contest hall have been working on 350 laptops. There's about 10% extra in case something breaks down. And we have about 80 laptops that are grading the solutions of the students. And something clever goes on there. So when you submit your solution, it needs to not be graded on a single test case. Sometimes we have 100 or 150 test cases that need grading. Every test case takes at most 1 second to grade. So you would think it would take, say 150 seconds to get your results back. But because we have 80 worker machines, 80 graders, what we do is we distribute all the test cases to all these workers, and depending on how busy they are, you could get your results instantaneously. Within 1 or 2 seconds, you would have the results. And as a contestant, this is great. This means you don't have to waste time. You submit, you press basically, and you get instant results and instant gratification. Just what people want to see these days. So once again, we're very, very happy that you're watching our live stream. We have over 9,000 viewers, which is great. There is a way to just type in the comment box. If you type something in English, we may be able to get to answer or get you a response on what's happening. And if not, then we'll just keep on talking. I am looking at my friends backstage. Do we have a camera feed? We have a camera feed from the hall. So this is it from me for today. Bye-bye. We'll see you in 2 days, and we'll go back to the contest hall where you can see the kids getting up and leaving. Thank you very much for watching.
Okay, everyone, we have finished everything. You can now leave the contest arena. Please leave the contest arena. The analysis and appeals will happen at 4. Analysis and appeals session will happen at 4. Please be back to the arena by 4. Please be back to the arena by 4 for the analysis and appeals session. Thank you. Have a nice lunch. The analysis and appeals session will begin at 4 at the arena. The analysis and appeals sessions will begin at 4 at the arena. The contest is over. The contest is over. Please leave the arena and go for lunch at the convention center. Please leave the arena and go for lunch now. You will be back here for an analysis session at 4. Everyone, please leave the arena. Thank you very much. Contest is finished. Please leave the arena. You will be back for the analysis and appeal sessions at 4. Please leave the arena at this moment.